NOAA is the National Oceanic and Atmospheric Administration, where we are a federal agency, part of the Department of Commerce. And part of NOAA's mission is to understand and predict changes in weather and climate, oceans and coasts. I work for the Oceanic and Atmospheric Research Line Office, which conducts science and research to improve the nation's weather forecasts. As the nation uses more wind and solar power, which are very dependent on the weather, we need improved forecasts of these generation sources of electricity. The power industry needs to understand how wind and solar resources and how much energy we can expect to get from them will change under various climate change scenarios. One of the challenges of forecasting winds, particularly the winds at the height of the wind turbines, is optimizing our forecast at that part of the atmosphere.
Wind profiling radars, they start to do measurements from 150 to 200 meters. It's slightly above rotor layer. And other instruments like buoy and tall towers, they provide information close to the surface. So if you will try to somehow interpolate this information to rotor heights, it could be incorrect. I work primarily with the LiDARs, and LiDAR is a remote sensing instrument similar to weather radars, except LiDAR is sending to the atmosphere a beam of light.
You can think of LiDAR very much like you think of a radar or sonar, where you send out a ping. You send out either in sonar, you send out a ping of sound and you wait for a reflection coming back, and you get information about how far away something is or where it is. With radar, you do that same thing, but you do it with radio waves. And with LiDAR, you do it with light. So you send out pulses of light and you get reflections back. So generally speaking, you reflect off the dust that's in the air. And the dust gets carried by the wind. And so we basically can use this instrument to visualize the wind field to study the wind field that we're looking at to understand better how turbines, wind turbines behave.
Forecasting solar radiance is something that NOAA has never really tried to do before. We just began this year in a project in collaboration with the Department of Energy and two private sector entities.
I work at the Global Monitoring Division. One of the key tasks of the Global Monitoring Division is to provide high-quality, long-term observations of key constituents of the atmosphere that affects air quality, climate, and weather. In our group, we are primarily concerned with solar radiation, and this is also one of the key things of the Solar Forecasting Improvement Project. One of the key issues with solar forecasting is the inherent variability of solar radiation that reaches the surface. And the inherent variability, the major factors are due to clouds. So a big part of this project is getting clouds right.
One of the things that makes it really tough to forecast solar irradiance on cloudy days is that we have to forecast precisely when a cloud will move by or form, or when a cloud will move away or dissipate. And we need to improve our fundamental understanding of clouds. This is a big area of science that, is just vast amounts of research need to be done.
Our state-of-the-art measurements are important for the Solar Forecasting Improvement Project because it provides model verification and data assimilation for these models.
The two models we develop are the Rapid Refresh, which is a 13-kilometer grid-scale model that spans entire North America. And there's a 3-kilometer high-resolution Rapid Refresh that just spans lower 48 states. So specifically what I do is the development of the physical parameterizations. And these are the representation of the subgrid scale weather processes in the model that can't be resolved by the model grid. We run these models for a lot of different case studies over long periods, retrospective periods, and we compare our model simulations against a variety of different platforms like satellite, radar, aircraft data, weather balloons, surface data, solar surf rad sites, tower data to get low-level winds. So we're constantly comparing our simulations against a variety of data
My role in designing the optimal energy plan for the nation is to build a simulator that mimics the US energy system, which incorporates large amounts of wind and solar power to cost optimize that network for the whole US. The main method we're using is a cost optimization algorithm to minimize the total cost for the entire energy system. And we've specifically designed it to work from the weather side, and so we're looking at variable generators such as wind and solar power. And we do the optimization over the US, which is approximately 8 million square kilometers. And so there is a huge amount of data, and because NOAA regularly uses large amounts of data for the weather modeling, we can leverage the computational resources here to be able to perform these optimizations effectively to solve the problem in a reasonable amount of time.
It's really crucial for NOAA to improve our forecast skill of wind and solar resources, because as the nation uses more wind and solar power, the grid operators need increased confidence in how much wind and solar power will be produced at varying time frames and in various locations.